At the edge of the known cosmos, the last galaxies shimmer like fading embers, suspended in an ocean of black. Their light has traveled for billions of years, yet even here, at the limits of sight, the universe does not end. It recedes further, into silence, into darkness, into something we cannot see. And here the mind hesitates, asking a question almost too vast to contain. If the universe is everything, how can it expand into something else? For centuries, humans believed the sky to be a dome, a shelter that enclosed the world. Later, it became an endless ocean of stars, infinite and unbroken. But the revelations of modern science tell another story. Space is not still. It stretches. Galaxies drift apart as though carried on the surface of a great, unseen tide. The universe itself swells with time, as though it is the interior of something larger, a fragile bubble growing within an invisible sea. Perhaps our cosmos is not the final stage, but only one chamber of a far grander architecture. A cell inside a cosmic body, a womb holding the seed of time and matter. If so, then what surrounds it? What holds us unseen, beyond the edges of perception? The thought is staggering, that everything known, every star, every planet, every light, be nothing more than the interior of a greater reality. Civilizations once asked, where are we in the universe? Today, the question deepens, what is the universe itself inside of? And as the galaxies slip away into the infinite dark, the haunting possibility remains, could our entire reality be the inside of something else? Long before telescopes revealed the true scale of the heavens, humanity raised its eyes to the night sky and saw mysteries painted in fire. To early civilizations, the cosmos was not empty space, but a living structure. The Sumerians imagined a dome of polished stone, a vault arching over the world. In ancient Egypt, the goddess Nut stretched her body across the sky, her form the very canopy of the stars. The Greeks envisioned crystalline spheres carrying the planets like jeweled lanterns, while in India the Vedas spoke of a cosmic egg, an eternal cycle of creation and dissolution, universes born and reborn in endless succession. Each myth, each vision, reflected a profound intuition that the cosmos was not merely out there, but enclosing, sheltering, containing. In their metaphors, one hears the first whisper of the possibility that the universe might itself be inside something greater. Aristotle shaped these dreams into philosophy. He argued that the heavens were finite, bounded by the outermost sphere of fixed stars, and that beyond this sphere there was nothing. Not empty space, not void, but pure absence. To imagine an outside of the universe, Aristotle said, was to imagine what could not exist. His cosmos was a closed vessel, self-sufficient and eternal, turning in perfect circles under divine order. This vision endured for nearly 2,000 years, a structure so complete that to question it was to question reality itself. Yet cracks appeared. The Hindu and Buddhist cosmologies of South Asia described countless worlds, layered in cycles of creation and destruction, a great breathing of time itself. In their view, universes were not singular but plural, arising and dissolving as easily as waves upon the ocean. These were not scientific theories, but they contained a radical thought that the cosmos we see could be only one instance, one expression inside a rhythm far larger than human comprehension. The ancients asked what lay beyond the stars. Their answers were poetic, spiritual, and symbolic, but they seeded the first human attempt to grapple with the greatest paradox. Can the universe, which is everything, be part of something greater still. It would take the birth of modern science to sharpen that question into something measurable, something testable. And yet, even in its precision, the mystery would only deepen. With the dawn of the scientific revolution, the cosmos was redrawn. In mechanical lines, Isaac Newton's Principia Mathematica revealed a universe governed by gravity, its motions precise, predictable, and eternal. Space itself, he argued, was absolute, a vast stage extending without limit in every direction, upon which stars and planets performed their endless dance. For Newton, the universe had no boundary, no edge, no outside. It was infinite, unchanging, held together by the invisible thread of gravity and the eternal laws of motion. This vision, at once liberating and unsettling, replaced Aristotle's finite spheres with an endless void. If the universe was infinite, then it needed no container, no exterior. But infinity is not easily grasped. The human mind strains against its edges, for infinity is as mysterious as nothingness. Where Aristotle had closed the cosmos tightly upon itself, Newton's cosmos dissolved its walls into a horizonless expanse. Yet both raised the same silent question: if the universe has no boundary, does that mean it exists inside nothing, or does it mean there is no outside to imagine at all? For centuries, Newton's picture held sway. It seemed confirmed by the regularity of the planets and the great clockwork of the heavens. But in the early 20th century, Albert Einstein shattered that clock. His general theory of relativity revealed that space and time were not rigid backdrops, but living fabrics, curved and warped by mass and energy. Space itself could bend, ripple, expand. Gravity was no longer a force acting at a distance, but the shape of space-time itself, guiding planets in their orbits and light in its path. The revelation was profound. For the first time, the universe was not a static stage, but a dynamic being. It could swell or contract, stretch or fold, like a living organism breathing through the ages. Reality itself was flexible. Suddenly, the question of whether the universe was inside something greater acquired new urgency. If space could change, could it also have an origin? Could it emerge from something beyond itself? The stage was set for one of the greatest discoveries of the 20th century, a discovery that would transform humanity's view of the cosmos forever. In 1929, the cosmos revealed its first whisper of secret motion. Edwin Hubble, peering through the 100-inch Hooker telescope at Mount Wilson, measured the light of distant galaxies. Their spectral lines stretched toward the red. Each galaxy appeared to recede, not randomly, but in proportion to its distance. The universe, once thought eternal and unchanging, was revealed to be expanding. Space itself was stretching, carrying galaxies like leaves upon a river that flowed outward in every direction. This simple observation transformed human understanding. The cosmos was not a static expanse, but a dynamic entity, growing from a denser past into a wider, ever-stretching present. The implications were staggering. If space was expanding, then once it had been smaller, compressed, infinitely dense, perhaps in a singular point from which everything had erupted. This was the seed of the Big Bang hypothesis, first suggested by Georges Lemaitre, a Belgian priest and physicist who saw in Einstein's equations the hint of cosmic birth. For the first time, humanity was confronted with the notion that the universe might have a beginning, a singularity from which all matter, energy, and space itself had sprung. And if it had a beginning, might it also reside within a larger structure, like a bubble in a vast and invisible foam? The expanding universe challenged not only mathematics but the imagination. Poets and philosophers found themselves grappling with the enormity of a cosmos that had once been smaller than an atom, yet now stretched across billions of light years. The paradox of scale became tangible. Human history, measured in centuries, unfolds within a universe billions of years old. Human perception, confined to a planet within a cosmos, vast beyond comprehension. And still, the universe's interior stretched relentlessly outward, hinting at boundaries that might exist only in abstraction, and horizons that our instruments could never pierce. Observers began to speak of cosmic horizons, the limits of what light and time could carry to our telescopes. Beyond these horizons, there may lie more galaxies, more stars, more worlds. Or perhaps, as some dared to imagine, there lay the outsider realm in which our universe itself was contained. The metaphor was poetic, yet precise, like an observer inside a soap bubble. One can see only the inner surface, yet the bubble itself floats in an invisible expanse. Could our universe then be a bubble adrift in a larger reality, a singular interior cradled within a greater whole? Hubble's discovery ignited not only science but the human psyche. The cosmos, once immutable and predictable, became an arena of mystery, a living question. It revealed a universe that was both finite in its past and unbounded in its future, stretching outward and into thought itself. And in that stretching, the question of what lay beyond the visible edge became unavoidable, haunting every attempt to measure or comprehend the infinite. The concept of the Big Bang carried with it an almost spiritual resonance. All matter, all energy, compressed into a singular origin point, a cosmic womb from which time and space emerged. The universe's expansion was not merely a physical process. It was a revelation of existence itself, a window into the processes that give birth to reality. It invited speculation that the universe might not be self-contained, but embedded within a larger arena, a context beyond observation. Could our cosmos be a singular chamber within a greater multiverse? Could the laws of physics we take for granted be the rules of just one interior space among countless others? The matter's singularity challenged the imagination. The universe, as we perceive it, is only a fragment of the full structure of reality. Just as the surface of a balloon appears boundless to a creature crawling across it, so too might our universe appear infinite, yet still be a finite interior, curved and contained within something higher dimensional. Einstein himself struggled with the implications of a beginning, seeking ways to preserve a steady, eternal cosmos. Yet the mathematics spoke otherwise. Space expands, time flows, and matter evolves in a cosmos with a definite past. The human, emotional reaction to this discovery was profound. For the first time, people realized that the universe was not an infinite, immutable stage, but a growing, changing entity. The cosmos could be both finite and eternal in ways the mind struggles to reconcile. This duality, small and vast, bounded and boundless, created a tension that has echoed through every generation of cosmologists since. The universe revealed itself as a puzzle, a mystery to be mapped, yet always retaining shadows beyond the reach of knowledge. Metaphors began to emerge naturally. The universe as a bubble, floating in a larger foam of unseen dimensions. The universe as a cell, a discrete interior with boundaries defined not by walls, but by the curvature of space itself. Observers realized that even as galaxies drift apart, as light stretches toward the red, there may exist a deeper level, an exterior, an environment from which our cosmos arose. And within that possibility lies the deepest philosophical challenge. The universe is everything we know, yet perhaps only a chamber in a far greater house. Cosmology was reborn. No longer a pursuit of certainties, it became a science of questions, of mysteries, of horizons. Every new observation, every distant galaxy, every measurement of cosmic microwave background radiation, every spectral line stretching across eons suggested that the universe was alive in its own temporal narrative, expanding not only in size but in the human imagination. The discovery of expansion forced scientists to rethink the concept of boundaries. Previously, space had been assumed to be a static, infinite canvas. Now, space itself was dynamic, capable of stretching, warping, and evolving. Einstein's equations predicted this possibility, and Hubble's observations confirmed it. Space was a living fabric, expanding from a dense origin point, carrying all matter with it. And if space could stretch, if time itself could unfold from an origin, then perhaps there is an exterior, a context beyond the observable cosmos. The metaphor of cosmic horizons became central. Light from distant galaxies takes billions of years to reach us. Beyond a certain limit, the universe is forever inaccessible, retreating faster than light can travel. This boundary is not physical, yet it functions as an edge to human observation. It hints at the possibility of an exterior domain, a realm in which our universe floats like a bubble in a higher dimensional sea. The mathematics of general relativity and modern cosmology allow for such possibilities, though they remain beyond direct detection. Even Newton's infinite cosmos, once imagined as boundless and unchanging, gave way to this new vision. The universe is finite in age but unbounded in extent. Its growth is both measurable and mysterious, expanding into a reality we cannot yet define. Early observers felt an almost existential awe. The cosmos is at once comprehensible and inaccessible, tangible in its laws yet elusive in its totality. The Big Bang is both a beginning and a doorway, a singularity that hints at something larger, something beyond the observable domain. The human response was visceral. The mind struggles with scale, with beginnings, with the notion that our entire cosmos could be but a part of a greater structure. Ancient myths, once dismissed as superstition, now echo in the mathematics of modern physics: the cosmic egg, the celestial dome, the layered cycles of Hindu cosmology. These visions were speculative, symbolic, yet they anticipated the scientific insight that the universe might be contained, finite yet growing, interior to something unseen. As instruments improved, the subtle fluctuations in the cosmic microwave background radiation revealed the earliest imprint of expansion. Tiny anisotropies, minute variations in temperature, marked the uneven distribution of matter in the young universe. These ripples, invisible to the naked eye, carried the fingerprints of cosmic history, encoded in light that had traveled nearly 14 billion years. They suggested that the universe had a definite origin, a starting point in time, and that its growth was not random but structured, patterned, perhaps guided by processes we are only beginning to understand. When Edwin Hubble's observations first revealed the universe was expanding, the response among scientists was not universal awe, but profound unease. For decades, the cosmos had been assumed to be either eternal or self-sustaining, and the sudden realization that it was growing, stretching outward from an origin, challenged the very foundations of scientific thought. The steady-state theory emerged as a reaction to this discomfort, proposing that the universe had no beginning or end, that matter was continuously created to fill the expanding space. To its proponents, the notion of a beginning was almost heretical. To admit a singularity, a point in which space, time, and matter condensed into infinitesimal density, was to confront the terrifying possibility of finitude. Scientists accustomed to seeing the cosmos as eternal recoiled at the idea of a boundary to existence itself. Einstein, who had once described a static, eternal universe, struggled with the implications of expansion. To preserve the immutability of the cosmos, he introduced the cosmological constant into his equations, an artificial force designed to counteract the tendency of gravity to collapse the universe. Yet this greatest blunder, as he later called it, hinted at the deep tension between observation and expectation. Science, it seemed, had opened a door that was difficult to close. The universe was not only changing, it was growing from a finite past, forcing human thought to confront questions once reserved for theology and philosophy. Fred Hoyle, a vocal opponent of the Big Bang concept, coined the term during a radio broadcast, intending to ridicule the idea that the universe had a single, explosive origin. Yet in doing so, he inadvertently named one of the most revolutionary scientific discoveries in history. The term Big Bang entered the lexicon, a metaphor that captured the drama, the violence, and the beauty of cosmic creation. Even those who resisted its implications could not escape the power of the imagery. A universe born from a point, expanding into the unknown, stretching the fabric of reality itself. For many scientists, the fear of finitude was as emotional as it was intellectual. A universe with a beginning implied an end, or at least a trajectory that was constrained by its initial conditions. Philosophers and physicists alike struggled to reconcile the enormity of space with the idea that it had a temporal origin. If all matter, all energy, all galaxies had emerged from a singular moment, then what came before it? Could there be a realm beyond the boundaries of our universe? A higher dimensional space in which the Big Bang itself was a local event, one bubble among many? The questions were both scientific and existential, blending mathematics with the human experience of awe, fear, and wonder. The balloon analogy, popularized in the early 20th century, captured the imagination. Galaxies scattered like dots on the surface of an inflating balloon, moving apart as the fabric stretched. The visualization was simple, yet it hinted at the profound mystery. If the surface expands, then what is the balloon itself inside of? Early physicists felt the unease of contemplating an unseen exterior, a domain beyond measurement, beyond understanding, and yet potentially crucial to the structure of the universe. Religious and philosophical debates intertwined with these scientific reactions. If the universe had a beginning, could it be interpreted as an act of creation? Some theologians saw the Big Bang as confirmation of divine intervention, while others worried that science had appropriated territory once reserved for spiritual contemplation. The idea of a universe as an interior of something greater, perhaps, inside the mind of a creator or the folds of a higher dimensional reality, became a topic not just for scientists but for thinkers across disciplines. Even as equations charted galaxies and cosmic expansion, humans could not help but ask the questions that had haunted them for millennia. What lies beyond? What contains everything we know? Could the cosmos itself be part of a larger structure? A reality in which our universe is only a local interior. Stephen Hawking famously posed the metaphorical challenge: what lies north of the North Pole? The question encapsulated the profound difficulty of imagining an outside to a universe that, by definition, contained all known space. If there is no exterior to the cosmos, then the universe is self-contained. Yet the mind naturally seeks an exterior, a context, a larger stage upon which this singular reality might be set. The tension between observable science and human imagination became acute. Mathematics could describe expansion, curvature, and cosmic horizons, yet it could not fully answer the deeper philosophical question of containment. Scientists slowly began to accept that their work might force contemplation of a beyond. The universe could be measured, mapped, and quantified, yet there existed the possibility of a domain that could never be directly observed. The expansion of space hinted at larger structures, perhaps dimensions beyond the three we inhabit, perhaps realities layered or nested in ways beyond immediate comprehension. Even the balloon analogy carried hints of this speculation. Dots moving apart on an inflating surface, suggesting an unseen environment, a medium in which the expansion occurs, and a reality that might contain our universe in ways that could never be fully measured. Yet despite the philosophical discomfort, scientific progress could not be halted. Observations of galactic redshift, cosmic microwave background radiation, and the uneven distribution of matter reinforced the reality of expansion. Resistance persisted, in part because the implications were unsettling. To accept a beginning was to acknowledge both finitude and contingency, to confront the possibility that existence might have a prior context, one that transcended space, time, and human perception. The human mind, trained to seek cause and effect, recoiled at the idea of a singular origin without a visible exterior. Early debates revealed the emotional dimension of discovery, fear of the finite, resistance to change, and awe at the scale and elegance of cosmic processes. The expansion of the universe was not merely a physical phenomenon. It was a profound, psychological event, reshaping humanity's conception of its place in reality. The first speculation that expansion might imply a higher dimensional reality arose slowly, cautiously, in whispered conversations among physicists. If space itself is stretching, if the universe is growing from a dense origin, then perhaps it is not an isolated entity but a portion of something larger, an interior of a greater geometry. The notion was daring, almost audacious, for it required thinking beyond the familiar three dimensions of length, width, and depth, and even beyond time as humans experience it. Mathematicians and theoretical physicists began to explore these possibilities through the language of tensors, manifolds, and multidimensional space, probing whether our observable universe could be a membrane, a brain, floating within a higher dimensional cosmos. The thought was intoxicating. We might inhabit not the totality of existence, but a localized chamber within a structure more vast than imagination permits. The balloon analogy captured this emerging idea in visceral, visual terms. Dots representing galaxies move apart as the surface inflates, suggesting expansion without requiring a center on the surface itself. It implies that the interior observers cannot see the full context. They can measure distances, curvature, but the environment in which the balloon exists remains inaccessible. Applied to the universe, this metaphor suggested that space could grow, carrying all matter, yet still be nested inside a larger, unseen domain. The paradox was both mathematical and philosophical. Expansion occurs without an apparent edge, yet the edge might exist in dimensions that our senses and instruments cannot access. Resistance remained, however. Too many physicists proposing a higher dimensional space seemed speculative, bordering on metaphysics. The discipline had grown accustomed to empirical evidence, to measurement and prediction. Hypothesizing a space beyond direct observation threatened the authority of experiment. Yet the equations permitted it, and gradually the scientific community acknowledged that some questions might not be answered with current instruments. The concept of an exterior, whether literal or abstract, became a necessary, if uncomfortable, companion to the understanding of cosmic expansion. Religious and philosophical discourse paralleled these debates. If our universe is inside something larger, could that something be conceived as divine, as an ultimate container within which all reality unfolds? The dialogue between science and spirituality deepened, not in conflict, but in shared recognition of the universe's mystery. Questions of creation, causality, and context intertwined with observations of redshifts, radiation, and galactic motion. Even in the sober, mathematical world of physics, imagination became essential. To comprehend a universe that expands and grows, humans were compelled to ask, what is the universe inside of, and what structures might exist beyond perception? Einstein's own discomfort with the implications of expansion remained a pivotal influence. Though he had initially introduced the cosmological constant to stabilize a universe he believed to be static, the mounting evidence of galactic recession and space stretching forced him to re-evaluate, observing that his equations predicted dynamic expansion. He had to reconcile intuition with mathematics. The universe was alive in its own geometric evolution. Space itself could curve, stretch, and warp. Time and matter were entwined in this motion, creating a cosmos that was neither fixed nor infinite in the simple sense, but structured in a way that suggested both beginning and boundary. Fred Hoyle's derisive coinage of Big Bang belied a deeper truth. The term captured the drama of cosmic birth in a single evocative image. The universe was not merely expanding, it had emerged explosively, releasing energy, matter, and the scaffolding of time from a point so dense that physics itself approached its limits. The metaphor carried scientific resonance, emphasizing the suddenness, the scale, and the profound significance of the event. While Hoyle intended mockery, the image became a lens through which generations would understand cosmic origin, the interplay of matter and space-time, and the unsettling possibility that our universe might be one of many, a single bubble in a higher dimensional foam. The fear of finitude persisted among scientists and philosophers alike. Accepting a beginning meant accepting contingency, the notion that existence could be framed by conditions beyond human experience. Before the Big Bang, questions arose. What preceded it, if anything? Could there exist a context beyond the observable universe, one that would reconcile the finite age of matter and space with the continuity of physical law? Theories of multiverses, higher dimensional spaces, and cyclic cosmologies began to emerge as tentative answers. Even speculation became an essential part of understanding, bridging observation with the human need to locate the universe within a larger conceptual framework. Observers turned to cosmic horizons as metaphors and tools. These horizons, the limits of what light and time allow us to perceive, created a natural boundary for measurement while hinting at the unknowable. Galaxies beyond these horizons move away faster than light can traverse the space, hidden from observation but mathematically inferred. In this sense, the universe has a shape, a limit to perception, and yet may exist within a larger structure that remains inaccessible. The analogy of the balloon became more than pedagogically. It represented the tension between measurable reality and speculative exterior, between the known and the unknowable. As scientific dialogue matured, the interplay between observation and theory became increasingly delicate. The discovery of cosmic microwave background radiation, though still decades away, was anticipated by theorists as a signature of the Big Bang. Even without these measurements, the implications of expansion were clear. The universe had a history, a measurable past, and the potential for boundaries beyond current comprehension. The idea that the cosmos might be an interior of something larger transitioned from speculative curiosity to a framework for serious consideration. It was no longer merely a thought experiment. It was a question with consequences for physics, mathematics, and philosophy. The human dimension of this reaction cannot be overstated. Scientists confronted not only equations, but their own perceptions of scale and existence. The universe, previously imagined as either eternal or infinite, was now both finite in age and unbounded in scope, stretching outward into domains beyond human reach. This duality, the known and the unknowable, generated emotional as well as intellectual tension. The realization that all matter, all galaxies, all observable history, might exist as a contained interior challenged the deepest assumptions about reality. Early speculations about higher dimensions gained traction because they offered a conceptual resolution to these paradoxes. If our three-dimensional universe is a surface of a four- or higher dimensional structure, then expansion can occur without requiring a center, without violating observable isotropy. The mathematics allowed it, and gradually, philosophical comfort grew alongside scientific rigor. Observers could imagine their universe as a bubble, a brane, or a segment of a larger topology, without abandoning empirical observation. The elegance of theory reconciled with the mystery of the unknown, and the first serious acceptance of a beyond entered the scientific mainstream. Religious and philosophical interpretations coexisted with these ideas. To speculate that the universe might be nested within a greater reality is to echo metaphors centuries old, from the cosmic egg of India to the layered spheres of medieval Europe. Science had transformed these poetic visions into questions of geometry, energy, and expansion, while retaining their awe-inspiring essence. In contemplating a universe contained within a larger structure, humanity confronted not only physics, but the emotional and philosophical implications of existence itself. By the mid-20th century, the scientific community had begun to recognize the inevitability of contemplating a beyond. Hubble's measurements, combined with relativistic cosmology, painted a picture of a universe expanding from a finite origin, yet appearing isotropic and homogeneous on large scales. This structure allowed for the possibility of embedding, for the cosmos to be an interior within a larger entity, and for human inquiry to explore boundaries that instruments could not yet probe. Questions that had once seemed metaphysical had become mathematical, while remaining profoundly mysterious. The analogy of the balloon remained central, refined in lectures, papers, and textbooks. Galaxies, as dots on a stretching surface, moving apart without a center, suggested expansion while hinting at an unseen exterior. The tension was conceptual and emotional. If the surface can grow, what holds the bubble? What contains the universe, and what larger reality permits its existence? Such speculation, once the province of imagination alone, became a necessary lens for understanding the cosmos. Even Einstein, who had resisted dynamic cosmologies, ultimately accepted the implications of expansion. His later reflections acknowledged the universe as a dynamic, evolving system with origins that demanded contemplation of the unknown. Hawking's provocative framing, asking what lies north of the North Pole, captured the essence of the challenge. The universe, in its entirety, is incomprehensible from within, yet its boundaries and growth suggest a context beyond observation. Early acceptance of these ideas marked a philosophical turning point. Science could no longer confine itself to the observable. It had to acknowledge the limitations of measurement and the possibility of a reality larger than the universe itself. The Big Bang was no longer merely a model, it was a gateway to speculation about multiverses, higher dimensional spaces, and the structures that might contain our cosmos. The dialogue between empirical evidence and philosophical reflection had begun, setting the stage for the next generations of cosmologists, mathematicians, and theorists to explore the ultimate question: what is the universe inside of? The first scientific reactions to expansion, fraught with resistance, humor, and awe, reveal a critical moment in human understanding. The cosmos, once eternal and immutable, became dynamic, finite in origin, and yet unbounded in its potential. Its expansion forced humanity to confront questions that blend physics, philosophy, and imagination, opening a path toward contemplating the universe as both everything we know and yet a contained interior, nested in something far greater than perception allows. In the early 1960s, a faint, persistent hum was detected in the static of a radio antenna at Bell Labs, a sound that seemed to come from everywhere and nowhere. Arno Penzias and Robert Wilson, initially puzzled and mildly frustrated, were uncovering what would become one of the most profound discoveries in cosmology: the cosmic microwave background radiation. This relic, a whisper of energy lingering from the universe's infancy, was the baby picture of all existence, a fossil light from nearly 14 billion years ago. Its uniform glow, permeating every corner of the cosmos, spoke of a universe that had once been unimaginably hot, dense, and simple. In capturing this radiation, humanity glimpsed the moment when space and time themselves began to unfold. A first tangible trace of a cosmic origin, interpreted through the lens of theory. The cosmic microwave background confirmed the concept of a singular beginning. It was as if the universe had imprinted its own origin into the fabric of reality, leaving a signature for future observers to read. No longer could expansion alone satisfy scientific curiosity. There was now evidence of a formative event, a point in which the known cosmos emerged from a more compressed, energetic state. This radiation, subtle yet pervasive, became a bridge between observation and theory, a medium through which the invisible past could communicate with the present. It was at once mathematical, physical, and almost poetically tangible, a whisper of time stretching across the void. Yet the data carried paradoxes as well as revelation. The horizon problem soon arose. If the universe began from a singular point, how could regions separated by billions of light years exhibit the same temperature and density? How could light, traveling at a finite speed, allow such distant areas to coordinate their properties? The smoothness of the cosmic microwave background implied a coherence that defied naive expectations of isolation. Scientists were confronted with a puzzle. The universe appeared finely balanced, uniform in ways that suggested unseen connections, a hidden order extending beyond the observable. The implications were as philosophical as they were scientific. If every region of space shared a subtle synchronization, then what unseen mechanism had imposed it? Was this a clue pointing toward a larger structure in which our universe itself is embedded, a process broader than direct observation. Early investigations revealed another mystery, the flatness problem. Measurements of space indicated a remarkable balance, a critical density that allowed the cosmos neither to collapse nor to expand uncontrollably. Space seemed tuned, poised, delicately at the edge between extremes. The odds of such precision arising by chance were staggering. Some theorists began to imagine mechanisms that could explain it, forces or processes operating beyond our direct perception. Subtle dynamics, shaping the entire universe from within. The idea of fine-tuning hinted at deeper structures, perhaps a multiverse or higher dimensional environment, within which our observable cosmos was a small, balanced chamber. Alan Guth, in the late 1970s, introduced inflationary theory to address these paradoxes. He proposed that a brief, extraordinary burst of expansion, faster than the speed of light, had stretched space in the universe's first fractions of a second. This inflation would naturally smooth out temperature variations, resolve the horizon problem, and account for the apparent flatness of space. The theory was elegant, mathematical, and profoundly unsettling. It suggested that our entire observable universe was the interior of a bubble, born in a vast, inflating sea of pre-existing spacetime. Each region could expand independently, potentially producing countless other universes, each its own bubble in an endless cosmic froth. The image of boiling water came to mind, each bubble representing a separate cosmos, isolated yet part of a larger process. Inflationary theory transformed the early investigations into something both scientific and philosophical. The mathematics was precise, testable through subtle measurements in the cosmic microwave background, yet the implications extended beyond empirical observation. Could our universe be only one among many? Could there exist an array of bubbles, invisible to us, each with its own origin and expansion, drifting silently in a higher dimensional medium? The questions blurred the boundary between physics and metaphysics, demanding both rigor and imagination. Cosmologists had to navigate a delicate line. Models had to predict observable phenomena, yet the broader context might remain forever inaccessible. Instruments like COBE, launched decades later, began to measure minute temperature differences in the cosmic microwave background, revealing the seeds of galaxies and structure. These tiny anisotropies confirmed that the universe had grown from an initially smooth state, yet retained the imprints of primordial fluctuations. Scientists realized that every pattern, every subtle variation, could be read as evidence of processes extending beyond local interactions. The universe was coherent on grand scales, uniform yet capable of forming galaxies, stars, and planets. The cosmic order seemed both emergent and finely tuned, pointing to mechanisms that might extend beyond the observable, beyond space and time. As directly experienced, human imagery became essential in these early investigations. The bubble metaphor captured the essence of inflation, the sense that universes could form, expand, and drift within a larger, unseen environment. Scientists spoke cautiously of multiverses, aware that the notion of other interiors, other universes, pushed against the limits of measurement, and yet the very act of framing the universe as a bubble suggested a profound insight. Expansion might not only describe our universe, but imply its containment, its place in a broader, perhaps higher dimension. Structure. The cosmos was no longer a solitary expanse. It had context, processes, and patterns that hinted at a reality beyond. Direct detection, the struggle to reconcile observation with speculation, defined the early investigations. Scientists wrestled with data, equations, and philosophical discomfort. Every measurement of radiation, every subtle anisotropy in the cosmic microwave background, was both a triumph and a reminder of mystery. The universe had revealed a history, a beginning, a coherence across unimaginable distances, yet it also suggested an exterior, a context that might never be fully grasped. Could the balloon of space be part of a larger medium? Could the bubbles of inflationary cosmology indicate a hierarchy of realities, nested structures, universes within universes? The questions transcended mathematics, entering the realm of human imagination, where awe, fear, and curiosity converge. The precision of modern instruments allowed scientists to test inflationary predictions, yet even confirmation reinforced the sense of mystery. The uniformity of the cosmic microwave background, punctuated by subtle variations, was a testament to processes both local and global, two mechanisms that shaped space before matter had coalesced into stars. Observers understood that these processes hinted at dynamics beyond the observable, the possibility that our universe was an interior region of a larger structure, influenced by conditions outside our perception. Every ripple in the primordial plasma became a clue, a message from a reality extending beyond what can be measured. The early investigations thus revealed a duality. The universe could be studied, quantified, and understood in part, yet simultaneously demanded contemplation of a beyond. Physics and philosophy converged in this recognition, as theorists explored higher dimensions, bubble universes, and cosmic inflation. The cosmos was not merely a backdrop for stars and galaxies. It was a process, a structure, a system with both measurable laws and mysteries that transcended observation. The universe, in its infancy, had left traces, echoes, and pattern signatures, not only of its origin, but perhaps of its embedding within something larger. The metaphor of boiling water, each bubble a universe within a larger pot, captured both scientific and emotional understanding. Humans could model, predict, and measure, yet the full context remained elusive. Each universe could be finite internally, yet part of an infinite ensemble. The early investigations were marked by this tension, the desire for empirical certainty, the recognition of cosmic beginnings, and the acknowledgement that the universe might be an interior to a process extending beyond the horizon of perception. In studying radiation, expansion, and inflation, scientists glimpsed not only the universe's origin, but also the profound possibility that what we call reality is only a chamber within a far greater, mysterious whole. As observational technology advanced, the universe revealed its subtle textures, patterns embedded in the cosmic microwave background that hinted at the processes shaping the very structure of reality. The tiniest temperature fluctuations, a few millionths of a degree, traced the seeds of galaxies and clusters, and by extension, the blueprint of cosmic architecture. Each variation became a cipher, encoding the history of expansion, the whispers of inflation, and the potential of structures beyond the observable horizon. Scientists began to realize that the universe was both self-contained and suggestive of an unseen exterior. The regularity and smoothness implied coherence across scales that could not be explained by local interaction alone. It was as if our universe carried within it the memory of a larger process, a pre-existing condition beyond the reach of instruments, yet fundamental to the formation of all matter and energy. This insight was both exhilarating and humbling. The smoothness of the cosmic microwave background implied a unity that seemed almost intentional, as though the cosmos were designed to maintain balance while allowing complexity to emerge. The flatness of space, measured with increasing precision, confirmed that the universe had been delicately poised from its earliest moments. Inflation offered a mathematical solution, stretching space to near-perfect flatness and explaining the uniformity of the background radiation, but it also hinted at the extraordinary scale of the larger environment. If our universe is a bubble expanding within a higher dimensional space, then its apparent harmony and balance are not accidental. They are imprints of forces and processes operating beyond observation, shaping the interior from the exterior, molding the cosmos from within a larger reality. The imagery of bubbles and boiling water became more than poetic metaphor. It became conceptual scaffolding. Each bubble in a pot of boiling liquid interacts subtly with its neighbors, bursts and reforms. By analogy, universes might form, expand, and exist as part of a greater structure, each internally coherent yet nested within a medium inaccessible to direct measurement. The idea that our universe could be only one among countless interiors sparked both wonder and apprehension. What was the pot containing these cosmic bubbles? Could there exist hierarchies of reality, layers beyond layers, each governed by similar physical principles yet invisible to our senses? The notion of a contained cosmos challenged intuition and forced a redefinition of what it meant for the universe to exist at all. In this period, the line between testable physics and philosophical reflection became porous. Theories had to remain mathematically consistent and observationally constrained, yet the implications stretched into territory that could not be measured. Not yet, perhaps never. The universe, as an interior, suggested a hidden order, a context larger than human perception. Scientists felt both liberation and anxiety, exhilaration at the possibilities, and the discomfort of confronting questions that might not yield empirical answers. The very act of imagining a reality beyond the observable universe became a rigorous exercise, balancing theory with speculation, mathematics with wonder, observation with philosophical courage. Kobe, the cosmic background explorer, and later Womp and Planck refined these investigations, mapping minute temperature variations with unprecedented precision. Each map, each contour of radiation, was a fingerprint of the universe's infancy, a record of density variations that would seed stars, galaxies, and clusters. The universe spoke through photons, encoded with the signature of primordial expansion. Yet these photons also whispered of context beyond detection. Observing inflation's imprint, scientists were able to trace the universe's earliest moments, confirming theories of rapid growth while leaving the larger, exterior questions tantalizingly unresolved. It was as if the universe had revealed part of its origin story while preserving the mystery of its surroundings. The horizon problem, so puzzling at first, became a window into higher dimensional speculation. Regions of space that should have been causally disconnected exhibited nearly identical temperatures. Inflation solved this by proposing rapid expansion, yet the implication was profound. Our observable cosmos might be a small segment of a much vaster environment, a single bubble in a sea of inflating space. Each bubble, potentially forming independently, could contain its own laws, constants, and structures. The imagery of a larger medium in which universes are born, float, and evolve became a foundational concept, guiding both cosmological theory and philosophical reflection. Humanity's home, it seemed, was not the entirety of reality, but a contained interior, floating in a process far beyond direct experience. The emotional resonance of these discoveries was immediate. Scientists confronted not merely equations, but the implications of scale and origin. To study the universe was to confront the limits of perception, the horizon of the observable, and the possibility that what is measurable is only a fragment of a greater, hidden whole. Each measurement, each refined map of microwave radiation, carried the dual weight of confirmation and mystery. Observers could reconstruct the universe's infancy with exquisite detail, yet the medium that might contain this cosmic bubble remained a realm of speculation, a shadow landscape at the edge of knowledge. Human imagination became entwined with rigorous science. Visual metaphors bubbles in a frothing pot. Balloons, expanding invisibly, were not mere pedagogical devices, but instruments of thought, shaping how theorists conceptualize structures beyond perception. The universe could be mapped, quantified, and modeled internally, yet its broader context required intuition, mathematical creativity, and philosophical openness. Early investigations demonstrated the power of evidence while highlighting the enduring mystery of containment. Our universe as an interior, a bubble, a chamber within an incomprehensibly vast process. By the end of the 1970s, the seeds of a new cosmic mystery had been planted. Inflation, cosmic microwave background observations, and the recognition of fine-tuning converged to suggest that the universe was not an isolated expanse, but a local interior within a larger process. Each discovery reinforced the notion that what we call reality might be one layer of nested structures, a single chamber within a greater architecture. The universe revealed its infancy in delicate radiation, its smoothness in tiny temperature variations, and its expansion as a signature of processes unfolding beyond direct observation. Scientists grappled with the philosophical consequences, even as they celebrated empirical triumphs. If our universe is a bubble, then the medium containing it may harbor other bubbles, other realities, perhaps obeying similar or radically different physical laws. The notion challenged intuition and demanded a reconception of existence, that reality might be layered, hierarchically structured, and that human observation is inherently local. While the mathematics allowed exploration of these possibilities, instruments remained confined to the interior, leaving the broader environment speculative but credible, grounded in theory yet beyond direct measurement. The imagery of bubbles and balloons provided both clarity and awe. Each expanding universe could carry within it coherent laws, structures, and histories, yet its exterior, the space in which it floats, remained hidden. Inflation suggested that such bubbles could be countless, forming continuously in a broader, higher dimensional medium. Our own universe, in this view, was not the entirety of existence, but a chamber within an extraordinary, dynamic process, one that might itself have no boundary, stretching indefinitely or nested within even larger structures. The interplay of observation, theory, and imagination created a tapestry of insight, revealing both the cosmos past and the tantalizing possibility of what lies beyond. Early investigations thus set the stage for the profound questions that would dominate modern cosmology. Radiation, expansion, and fine-tuning provided evidence not only of origins but of context. The universe, in revealing its infancy, hinted at a larger framework, a structure in which observable reality is an interior, a portion of something more expansive, layered, and intricate than previously conceived. The work of scientists from Penzias and Wilson to Guth and beyond created the first tangible bridge between the observable cosmos and the philosophical contemplation of what lies beyond a universe at once known and mysterious, finite internally, yet suggestive of an infinite exterior. The chapter of early investigations closes on a note of both triumph and wonder. Humanity had captured the first signals from the universe's birth, traced the outline of its earliest expansion, and glimpsed the potential of a larger process encompassing all that we observe. Yet the medium, the context, the outside of the cosmic bubble remained elusive, whispering of realities beyond measure, challenging the mind and inviting generations to imagine, calculate, and reflect. The universe had begun to tell its story, but its full narrative, and the story of the space that contains it remained, as ever, a mystery dot in the quiet of space. Above the atmosphere and its cacophony of terrestrial noise, the Wilkinson Microwave Anisotropy Probe, WMAP, began its patient vigil. Orbiting Earth, it mapped the cosmic microwave background with unprecedented clarity, capturing the faint afterglow of the universe's infancy. Each measurement, each photon, became a brushstroke in an intricate portrait of creation. The universe revealed itself not as a uniform expanse, but as a tapestry of subtle variations, temperature differences that traced the primordial seeds of galaxies, clusters, and cosmic structure. It was a map not merely of space, but of time, frozen in radiation that had traveled nearly 14 billion years, carrying the echoes of expansion, the whispers of origin, and the ghostly imprints of processes that shaped reality itself. With WMAP came Planck, a satellite designed to refine this map, pushing precision to limits previously unimaginable. The cosmic microwave background was no longer a diffuse glow. It was a detailed mosaic, each variation measured in millionths of a degree. These fluctuations spoke volumes about the early universe, confirming predictions of inflation and revealing anomalies that defied easy explanation. Among these was the discovery of cold spots regions, slightly cooler than their surroundings, mysterious in scale and pattern. Some theorists propose that these anomalies might hint at cosmic interactions beyond our own universe, a silent fingerprint of collisions with other universes or domains born from the same inflating field. The very fabric of the cosmos seemed to carry evidence not only of its internal processes, but of a broader reality in which it was embedded. These observations, breathtaking in precision, reinforced a growing sense that the universe was at once knowable and enigmatic. Expansion was no longer a simple stretching of space. It was a dynamic, evolving process, now measured with confidence. The contours of matter and radiation suggested structure, coherence, and an intricate order, yet they also revealed boundaries that hinted at phenomena beyond direct observation. The cold spots and subtle anisotropies were more than curiosities. They were messages from a cosmos that could not be contained within the limits of human expectation. Each new map of the microwave background suggested that the universe might be a bubble within a larger field, a chamber in a process extending beyond perception, raising profound questions about origin, containment, and the very nature of existence. The universe surprised again in 1998, when two independent teams studying distant supernova revealed an astonishing truth. The cosmos was not merely expanding, but accelerating. Space itself was being stretched by a force unknown, a phenomenon that would come to be called dark energy. This discovery, defying prior assumptions, suggested that the universe's evolution was governed by something beyond visible matter, radiation, or even the familiar laws of gravity. Dark energy became a symbol of the limits of human knowledge, an invisible hand shaping the cosmos while eluding every instrument. Its discovery reinforced the idea that our universe might be a local interior within a larger, more complex reality, influenced by forces and structures beyond immediate perception. The idea of a multiverse gained momentum alongside these breakthroughs. If inflation is correct, then countless universes might exist as bubbles within a larger inflating field, each emerging independently yet subject to similar physical laws. Our universe, in this vision, is not unique but one among a vast ensemble, its properties dictated by the conditions of its birth and its interior dynamics. The metaphor of bubbles in a boiling liquid remained apt, each universe coherent internally but nested in a medium beyond observation. Cosmic collisions or imprints from adjacent bubbles might account for anomalies such as cold spots in the microwave background, suggesting that our universe is not isolated but dynamically entwined with a larger architecture. Black hole thermodynamics added a new layer to this contemplation. The discovery that black holes possess entropy, temperature, and even radiation implied that the interior of a black hole could, in principle, be a universe unto itself. Some theorists speculated that our cosmos might resemble the interior of a black hole existing within a higher dimensional space, its own laws and constants emerging from the dynamics of a parent structure. Penrose extended this thinking with conformal cyclic cosmology, proposing that universes might emerge from the death of prior ones, endlessly cycling through creation and collapse. Each theory, rooted in mathematical rigor and observational hints, suggested that the universe we inhabit might be only one chapter in a story extending far beyond its visible boundaries. The holographic principle emerged as a radical refinement of these ideas, proposing that the information contained within a volume of space could be encoded on its boundary. Space itself, in this view, might be a projection of a higher dimensional reality, a three-dimensional interior generated by dynamics operating on a surface beyond direct perception. If correct, this principle implied that the universe is a kind of cosmic projection, a contained reality whose structure and evolution are determined by laws and information, existing outside the space we perceive. It was a profound shift, challenging notions of substance, dimension, and containment, and suggesting that our universe might be an interior in the most literal sense, emergent from a higher order. Geometry, observational instruments continued to probe deeper. From the Hubble Deep Field to the James Webb Space Telescope, revealing galaxies, star formation, and the cosmic dawn with unprecedented clarity. Each new image, each newly mapped region, reinforced both understanding and mystery. Humanity could reconstruct the universe's early evolution, measure the distribution of matter and energy, yet the questions persisted. Why these initial conditions? What process governed the uniformity, the flatness, the balance? Every breakthrough, while clarifying local structure, pointed to larger unknowns, suggesting that our universe is nested in a broader framework, shaped by influences beyond direct measurement. Each discovery reinforced the notion that our cosmos is both knowable and mysterious. The anomalies, the accelerating expansion, the imprints of inflation, and the possibility of projection from a higher dimensional field collectively suggested that our universe is a local interior, a finite but dynamic chamber within a larger process. Scientists were compelled to ask daring questions. Might reality itself be embedded in a geometry more complex than can be directly observed? Could universes be born, expand, and evolve within higher dimensional spaces, each with its own history yet constrained by overarching processes? The cosmos, in revealing its earliest photons and subtle fluctuations, hinted at an architecture beyond our instruments, a reality in which our universe is contained yet coherent, finite yet unbounded. As observations deepened, the universe revealed more subtle and confounding features. The Planck satellite mapped the cosmic microwave background with exquisite resolution, confirming inflationary predictions while uncovering anomalies such as the cold spot, a region of lower temperature than surrounding space. Some researchers speculated that this could be the imprint of a collision with another universe, a distant bubble overlapping with our own in a higher dimensional, inflating space. The notion was unsettling yet compelling. The cosmos, once imagined as isolated and self-contained, might be interacting with structures beyond comprehension. Each cold spot became a question carved into the fabric of space-time, a silent witness to processes and realms beyond the observable horizon. The accelerating expansion of the universe intensified these reflections. Dark energy, dominating the cosmic balance, suggested that the universe's fate is governed by forces that elude direct measurement yet dictate large-scale dynamics. The idea that space itself could stretch, expand, and accelerate without a visible cause pointed to a deeper substrate, a reality underpinning the cosmos that might be higher dimensional, unseen, and fundamental. The universe, in this vision, is not merely expanding internally, it is a dynamic interior, influenced by processes beyond its apparent limits. The implications were profound. Our observable cosmos could be a local region of a grander architecture, a bubble evolving within a medium that contains countless others, each potentially with its own laws and histories. Black hole thermodynamics offered another extraordinary perspective. Stephen Hawking's discoveries revealed that black holes radiate energy, possess entropy, and encode information in their surfaces, suggesting that the interior of a black hole could, in principle, form a self-contained universe. Some theorists propose that our universe itself might exist as the interior of such a structure, its physical constants and emergent laws a consequence of dynamics occurring in a parent dimension. Penrose's conformal cyclic cosmology further suggested a succession of universes, each emerging from the death of its predecessor, with time itself stretching into cycles beyond direct observation. In these models, our cosmos is both a product and participant, an interior world carrying echoes of prior realities while gesturing toward future ones. The multiverse concept, long speculative, gained serious traction. If inflation produces countless bubble universes, then our observable universe is one chamber among many, a finite interior in a sea of potentialities. Each universe could be internally coherent, obeying predictable laws, yet exist in a vast landscape inaccessible to direct measurement. The imagery of bubbles and inflating fields became not mere metaphor, but a framework for understanding containment, origin, and interaction. Scientists were beginning to accept that the observable cosmos is a local interior with boundaries, defined not by edges in space, but by the limits of causal influence and measurement. Reality itself might be a nested hierarchy, layers of interiors within a broader, invisible structure. The holographic principle intensified this sense of nested reality. The proposal that information within a volume of space could be encoded on its boundary implied that the universe might be a projection, an interior generated from higher dimensional data. Space itself could emerge from processes existing outside. What we perceive, a three-dimensional tapestry woven from a higher-order substrate. This radical idea reframed cosmology. The universe is not simply a self-contained arena, but an interior manifestation of a deeper, more complex geometry. Observations from WMAP, Planck, and Hubble provided the empirical scaffolding, while theoretical frameworks suggested that the cosmos is embedded, contained, and emergent, a local interior of something far larger and richer. Instruments probing deeper into cosmic history reinforced the mystery. The Hubble Deep Field captured galaxies forming billions of years ago, while the James Webb Space Telescope glimpsed the earliest stages of star formation and cosmic dawn. Each observation revealed the intricacy and coherence of the universe, yet also its incompleteness. Beyond these distant objects, beyond measurable photons, lies the unobservable medium in which our universe may reside. Every discovery confirmed the internal consistency of our cosmos, while simultaneously hinting at influences beyond the observable boundary, forces shaping the interior from a hidden exterior. These breakthrough observations reshaped the philosophical landscape of cosmology. Scientists now confronted a reality in which measurable expansion, inflationary imprints, and anomalous cold spots suggested both isolation and embedding. The universe was no longer a solitary continuum, but a local interior, a chamber of coherent structure within a broader and possibly infinite environment. Questions once considered metaphysical were now subject to scientific scrutiny. Could the universe be the interior of a black hole, a projection of a higher dimensional surface, or a bubble in an inflating multiverse? Each hypothesis, grounded in data and mathematics, pushed the boundary between measurable physics and speculative reflection. The tension between empirical evidence and cosmic imagination defined this era. Observers could measure and model, reconstruct the universe's history with unprecedented detail, yet the larger environment remained elusive. Every anomaly, every subtle temperature fluctuation, became a clue to processes beyond perception. The universe spoke not only of its birth and evolution, but of its potential embedding, suggesting that the observable cosmos is an interior, a contained system reflecting influences and structures invisible yet fundamental. Humanity's understanding was expanding, yet with every layer revealed came a deeper layer of mystery. By the turn of the 21st century, cosmology had entered a new realm of audacious inquiry. Dark energy, inflation, and cosmic microwave background anomalies compelled theorists to contemplate the universe as a local interior embedded within a higher-order reality. Each discovery, while confirming the internal coherence of the cosmos, reinforced its context within a larger, inaccessible structure. Observations of expansion, temperature fluctuations, and early galaxies revealed not just what the universe was, but hinted at what it might be contained within. The metaphor of bubbles and inflating fields, once poetic, now guided scientific thinking. Each bubble universe could expand independently, yet exist in a higher dimensional medium influencing its birth and evolution. Collisions between bubbles might leave traces in radiation, subtle anomalies detectable with precise instrumentation. Cold spots and variations in the cosmic microwave background became possible signatures of these hidden interactions. Every map, every observation, revealed coherence internally and hinted at a surrounding structure, an outside shaping the interior from a distance. Penrose's cyclic cosmology and the holographic principle suggested even more radical possibilities. The universe might emerge from the collapse of previous cycles, or from the boundary of a higher dimensional space. Reality could be a projection, a local interior generated by information encoded elsewhere, with the laws of physics arising from processes beyond immediate observation. Such ideas challenged intuition, yet were grounded in rigorous mathematics, and supported by increasingly precise measurements. Observers could no longer conceive of the cosmos as isolated. It was internally consistent, but contextually nested, finite within, and yet suggestive of infinite containment. The Hubble Deep Field and James Webb observations reinforced both clarity and wonder. Galaxies forming billions of years ago illustrated the internal evolution of our universe, yet beyond them lay an expanse, invisible and potentially infinite. Each breakthrough reinforced the notion that the cosmos is a contained interior, shaped by forces and structures beyond observation, a dynamic chamber of reality within a broader architecture. Science had illuminated the interior, yet the surrounding context remained tantalizingly beyond reach, a horizon that framed both knowledge and mystery. Breakthrough observations had transformed cosmology into a science of interiors, expansion, anomalies, dark energy, black hole, thermodynamics, and higher dimensional projections all converged on a singular, profound insight. Our universe is a local interior, coherent and structured, yet embedded in a larger, mysterious reality. Each discovery did not merely answer questions, revealed larger unknowns, compelling humanity to confront the possibility that what we observe is a finite chamber, a bubble, a projection, all nested within the vast, enigmatic beyond of existence. The universe, in revealing itself, had opened a window onto its own containment, hinting at realities far greater than human perception and inviting reflection, wonder, and perpetual inquiry. The universe, in its vastness, continues to conceal as much as it reveals. As astronomers mapped the motions of galaxies, they uncovered a profound anomaly. Stars moved not only according to the gravitational pull of visible matter, but with speeds that defied expectation. This invisible influence, later termed dark matter, forms an unseen scaffolding, a cosmic web that cradles galaxies and clusters, shaping the architecture of the universe. Though unseen, its effects are undeniable. The spirals of distant galaxies trace the contours of a substance we cannot detect directly, yet it dictates their dance, their rotations, their very cohesion. It is as if the universe has built a framework. In shadow, a hidden lattice holding the visible in delicate suspension. Dark energy adds an even deeper layer of mystery. In 1998, the universe's accelerating expansion revealed that a force unknown, pervasive, enigmatic was stretching space itself faster and faster. While gravity works to pull matter together, dark energy pushes outward, dominating the cosmos at the largest scales. Together, dark matter and dark energy constitute roughly 95% of the universe's content, leaving ordinary matter, the stars, planets, and galaxies we can see as a mere trace. This stark discrepancy challenges both imagination and intuition. The observable universe is only a veneer, a thin membrane covering a reality dominated by the unseen. The cosmos, it seems, is shaped primarily by what cannot be measured directly. A profound reminder that the interior of reality is more than the sum of its visible parts. Speculation emerges naturally from these anomalies. Could dark matter and dark energy be hints of higher dimensional structures? In string theory and related models, The idea of a brain world suggests that our universe is a membrane, a three-dimensional sheet embedded in a higher dimensional space. Forces, particles, or phenomena leaking from these extra dimensions might manifest as the gravitational pull of dark matter or the expansive push of dark energy. The poetic image is irresistible. A fish swimming in a pond cannot see the air above. Yet the air shapes the surface, creates ripples, and allows the pond to breathe. So too, perhaps, is our universe shaped and constrained by a medium beyond perception, a surrounding reality whose effects are visible while the substance remains concealed. Observational limits frame this mystery in stark relief. The universe has horizons, cosmic boundaries beyond which light has not yet reached us. These horizons define the observable universe, but they do not define existence itself. Beyond them may lie regions, structures, or even other universes that we cannot see, their influence detectable only indirectly, if at all. The cosmic microwave background sets a boundary, a surface beyond which our instruments cannot measure. Yet anomalies within this radiation suggest interactions, collisions, or forces originating beyond what we can observe. Humanity's perception of reality is therefore necessarily local, a window onto an interior that may itself be a fragment of a vaster whole. Quantum entanglement offers a subtler yet no less profound clue. Particles separated by light years can exhibit correlations that defy classical explanation, their properties linked instantaneously across space. While this does not allow communication faster than light, it hints at a deeper, underlying structure in which space itself is less absolute than once thought. Could these quantum connections be the threads tying our universe to a higher dimensional framework? The possibility is tantalizing. Entanglement, black holes, dark energy, and cosmic structure collectively suggest that reality is a layered interior, with visible phenomena only the surface of a far richer architecture. Black holes, paradoxical in their nature, emphasize the tension between interior and exterior. Their event horizons mark the boundary where space and time bend toward singularity. Information may be encoded at their surfaces, suggesting that what lies within is both contained and emergent. Some theorists speculate that black holes could open into other regions or universes, offering a glimpse of an interior nested within an even larger structure. Each of these discoveries, from dark matter to quantum entanglement, pushes the human mind to confront the unsettling possibility. Our universe may be forever bounded by horizons we cannot cross, enclosed within walls of space-time that hide the larger reality. The combined weight of dark matter, dark energy, quantum paradoxes, and black hole enigmas reshapes the philosophical landscape. Our interior universe is coherent, structured, and elegant, yet it exists largely as a shadow of what may surround it. Scientific instruments have illuminated its contours, traced its history, and mapped its evolution with extraordinary precision. But the medium in which it is embedded remains speculative. Could unseen dimensions, higher order spaces, or neighboring cosmic bubbles influence its form? Each hypothesis is grounded in mathematics and observation, yet all lead to a profound sense of incompleteness. The universe reveals its internal logic while withholding the context that gives that logic its ultimate meaning. The brain world scenario captures this tension poetically. Our three-dimensional universe, like a membrane, might float within a higher dimensional expanse. Forces emanating from outside this membrane, leaking gravity, subtle curvature, or hidden energy, could explain the phenomena of dark matter and dark energy. Just as the surface of a pond responds to unseen winds above, so too might the interior of our universe respond to the dynamics of an embedding space. The cosmos, in this vision, is both a contained interior and an open system, influenced by a realm that is inaccessible yet intimately entwined with its structure. Each observational advance has reinforced this sense of layered reality. WMAP, Planck, Hubble, and now the James Webb Telescope have unveiled the universe's history, tracing the formation of galaxies, stars, and the first cosmic structures. Yet every horizon crossed, every photon traced back to the dawn of time, emphasizes what remains unseen. The cosmic walls may be impenetrable, and the surrounding medium, if it exists, may forever elude direct observation. Humanity glimpses only the interior, yet the interior itself hints at the extraordinary possibility of a larger, more profound context and architecture whose scale and complexity surpass comprehension, and whose influence is felt in every galaxy, star, and quantum fluctuation, dark matter, and dark energy define not only the structure of the cosmos, but the boundaries of human perception. Galaxies swirl and clusters form in patterns dictated by forces we cannot see, while the universe accelerates outward, as though propelled by an invisible hand. The overwhelming majority of reality, it seems, exists in forms undetectable by conventional instruments, a reminder that knowledge is limited to the interior of observation. Every discovery reveals coherence and elegance, yet every solution deepens the mystery. Why this distribution? Why this acceleration? Why this particular set of laws within a universe largely invisible in its composition? The cosmos, in exposing the hidden, emphasizes both our understanding and our ignorance, showing that the interior we inhabit is part of a larger, unknowable framework. The brain world concept from string theory captures the imagination with its startling implications. If our universe is a membrane floating in higher dimensional space, the familiar forces gravity, electromagnetism, the nuclear interactions may be localized to this membrane, while other influences seep in from unseen dimensions. These interactions could manifest as the phenomena we attribute to dark matter or dark energy, subtle hints of a reality outside our reach. The metaphor of a fish in a pond again resonates. The fish experiences a coherent world, yet every ripple, every wave is influenced by forces it cannot perceive. In the same way, our universe may be a coherent interior shaped by conditions and processes beyond observation. A local reality nested within a more expansive cosmos. Observational horizons underscore this limitation. Light has traveled for 14 billion years, yet beyond the visible universe lies territory inaccessible to any instrument, causally disconnected from our own. These cosmic boundaries define what can be known, but not what exists. The universe, in this sense, is both bounded and unbounded, bounded in observation, unbounded in speculation. Scientists must extrapolate, using anomalies, background radiation, and the distribution of matter to infer the existence of structures beyond direct measurement. Each inference deepens the mystery, suggesting that while the interior is mapped and understood, the exterior, the surrounding reality, remains fundamentally unknowable. Quantum entanglement further complicates the picture. Particles separated by vast distances exhibit correlations that defy classical logic, as though connected through a hidden scaffolding underlying space itself. These instantaneous relationships hint at a deeper order, a substrate connecting disparate points of the interior universe, possibly linked to higher dimensional structure. Entanglement suggests that even in the perceived emptiness between galaxies, the interior of the cosmos is suffused with connections, hinting at something greater. It is as if the universe contains threads extending beyond its observable volume, linking the interior to forces and structures whose origin may lie outside space-time as we know it. Black holes. To illuminate this paradox, the event horizon marks a point of no return. Yet theories suggest the interior may contain entire universes, isolated from ours, yet dynamically connected through gravitational and quantum processes. Information encoded on the surface hints at emergent interiors and hidden geometries. If our own universe were a similar interior, the cosmic horizon could be the boundary of a higher dimensional domain, and everything observable within it would be shaped by processes beyond direct detection. Each black hole becomes a mirror, reflecting the potential of our universe to be simultaneously finite, contained, and part of a larger, hidden structure. Cosmic observations and theoretical advances converge on an unsettling possibility. The universe we inhabit is a local interior, bounded by horizons we cannot cross, shaped by forces and structures that may remain forever inaccessible. Dark matter and dark energy, quantum entanglement, and black hole interiors all suggest that reality extends beyond what can be measured, that the visible universe is a chamber within a larger architecture. Scientific instruments illuminate the interior, yet the surrounding medium remains speculative, the unseen influencing the seen. Humanity's understanding is partial, framed by the interior we observe while hinting at a grandeur beyond perception. The poetry of this perspective is undeniable. Our universe, elegant and self-contained, is also a shadow of a larger reality. It is structured, coherent, and bound by laws we can measure, yet its shape, expansion, and internal dynamics suggest the presence of something beyond. Brains, bubbles, extra dimensions, and entangled quantum threads all converge toward the vision of a cosmos that is simultaneously finite and infinite, interior yet part of a greater whole. Every observation, from the swirling galaxies to the faint background radiation, is a window into an interior whose contours reflect influences from a larger, inaccessible reality. The cosmic horizon stands as both limit and invitation. Beyond it, the universe may continue, connected to higher dimensional fields, neighboring bubbles, or domains inaccessible to direct observation. Dark matter and dark energy are the fingerprints of this hidden structure, subtle yet pervasive. Quantum entanglement and black hole interiors suggest that even within the interior, connections extend beyond the apparent boundaries, pointing to a deeper, underlying geometry. The universe, in revealing its internal logic and its subtle anomalies, gestures constantly toward a surrounding medium, a framework whose existence is inferred, its nature unknowable yet profoundly influential. Humanity, perched within this interior, contemplates the vastness beyond. Instruments extend perception, mathematics stretches understanding, yet the cosmic walls may be unbreachable. The universe, in all its elegance and precision, is at once a coherent chamber and a fragment of a larger, mysterious architecture. The mystery deepens not only because of what we do not see, but because the very structure of reality hints at a surrounding order vast, hidden, and beautiful. To live within the universe is to witness its interior, but to reflect upon its unseen exterior is to glimpse the sublime, a reality greater than imagination, structured beyond perception and forever inviting curiosity, wonder, and reflection. At the frontier of understanding, science presses against the walls of the known universe, probing the boundaries where observation, theory, and imagination converge. Cosmic inflation, the rapid expansion that propelled the universe from a singular point to a vast expanse in fractions of a second, is now a central focus of exploration. Physicists seek the faint echoes of this primordial growth in gravitational waves, ripples in the fabric of spacetime itself. Instruments such as LIGO and future space-based observatories aim to detect these subtle vibrations, a whisper from the universe's infancy. Each potential detection is not merely confirmation of inflation. It is a glimpse beyond the observable interior, a signal hinting at processes in a larger cosmic landscape, perhaps even interactions with realms beyond our universe. Simultaneously, the cosmic microwave background remains a canvas for extraordinary speculation. Tiny irregularities in this ancient radiation may encode the fingerprints of other universes. Scientists have searched for anomalous patterns, cold spots, or alignments that cannot be explained by conventional inflation alone. These deviations are interpreted as potential scars left by collisions with neighboring bubble universes in an inflating multiverse. The imagination is constrained by data, yet guided by the mathematical elegance of theory, a universe within, an interior that is itself one among many, a bubble floating in a higher dimensional field. Observation becomes an act of detective work at the very edge of comprehension, where subtle clues may point to a reality larger than the cosmos we can measure. Particle accelerators push this quest into the laboratory, recreating conditions that may reveal extra dimensions. Collisions at the LHC probe energy scales, where hidden spatial dimensions could subtly influence particle behavior. If additional dimensions exist, their presence might be detected indirectly through deviations from expected outcomes, missing energy, or novel particles. The universe, in this vision, is not a solitary interior but a chamber embedded in a higher dimensional expanse. The laboratory becomes a speculative telescope, a human-made portal into dimensions that are otherwise inaccessible, a place where equations and observations meet at the edge of possibility. Beyond laboratories and telescopes, theorists explore wormholes and higher dimensional geometries as mathematical laboratories for the imagination. These structures, solutions to Einstein's equations and extensions in string theory, suggest pathways between regions of space-time or even between universes. While physically unconfirmed, they provide conceptual tools to imagine how our interior universe might connect to a larger cosmos. Simulations indicate that if bubble universes collide, they could leave detectable imprints on the sky. Subtle distortions or temperature anomalies in the cosmic microwave background. Each simulated collision is both a story of creation and a whisper of the unseen. The interior universe bears traces of encounters with a surrounding expanse, hints that the local reality is sculpted by interactions beyond perception. Quantum cosmology pushes even further, contemplating the universe as a quantum fluctuation within a larger field. This radical notion frames our cosmos as a local excitation, transient yet structured, emerging from a probabilistic vacuum. Space itself is born from fluctuations in a primordial quantum field, creating an interior of coherent structure that is both real and ephemeral. The idea is mathematically rigorous yet empirically elusive. Observations can confirm only indirect consequences, shadows of phenomena occurring in domains beyond direct measurement. Humanity glimpses the interior, yet the exterior, the surrounding. Reality is accessible only through the constraints of mathematical consistency and theoretical plausibility. speculations extend to black holes as cosmic laboratories. Some theories propose that universes could emerge within black holes, their interiors unfolding in ways inaccessible to an external observer. If true, our own universe might exist inside such a structure, constrained and shaped by dynamics occurring outside our perception. This hypothesis transforms the familiar into the extraordinary. The cosmos is not merely an interior of space and time, but a nested interior, connected through gravitational and quantum pathways to a larger, enigmatic environment. The universe becomes both tangible and profoundly mysterious, a structure whose boundaries are mathematical, physical, and philosophical. Mathematical beauty drives much of this exploration, yet it collides with the practical limits of empirical. Theoretical constructs brain worlds, bubble collisions, quantum fluctuations possess internal consistency, elegance, and symmetry, yet confirming them in the laboratory or through observation remains daunting. The universe has become a stage for the interplay between equations and evidence, where human ingenuity confronts the finite scope of measurement. Scientists navigate this tension, balancing the poetic implications of theory against the disciplined rigor of observation. Each equation, each simulation, is a bridge between the interior we can observe and the exterior we can only infer, a pathway toward understanding that must respect both empirical reality and imaginative possibility. At this extreme edge, humanity stands metaphorically at a cliff. The observable universe is beneath the feet, measured and mapped with exquisite precision, while the unknown extends above and around, invisible yet undeniably influential. Gravity, dark energy, quantum fields, and higher dimensional possibilities all hint at forces shaping the interior from beyond. Instruments, telescopes, accelerators, and satellites illuminate only a fraction of this structure, and yet the mere act of observation reveals the subtlety, coherence, and interconnectedness of what might otherwise be considered chaos. The cosmos is a contained interior, yet its boundary gestures ceaselessly toward something greater. Scientists are both explorers and poets at this frontier, seeking patterns in the sky and the laboratory while contemplating realities inaccessible to sense or instrument. Each discovery reframes the interior, revealing new layers of complexity and connection. The universe, in its vastness, becomes a mirror reflecting both human curiosity and the profound limitations of perception. On this extreme edge of science, knowledge is incomplete, yet the pursuit itself illuminates the contours of the interior and the whisper of an exterior, offering glimpses of a reality that transcends observation and hints at infinite possibility. The search for gravitational waves from cosmic inflation represents a delicate listening to the heartbeat of creation itself. These faint ripples, traveling across the cosmos for nearly 14 billion years, carry information about the universe when it was smaller than an atom, expanding faster than the speed of light. Detecting them is akin to hearing the whisper of the cosmos before time had fully begun. Each potential signal is not merely a confirmation of inflationary theory. It is a message from a domain beyond the interior, hinting at processes and structures. In a meta-reality in which our universe is but a chamber, the faint undulations in space-time become bridges, connecting human instruments to the echo of creation and suggesting the presence of phenomena entirely inaccessible to direct perception. Simultaneously, the cosmic microwave background offers a subtle diary of the universe's early moments, a frozen record of light released when the cosmos was still young. Researchers search for anomalies, patterns that deviate from smoothness, minute imprints that might betray collisions with other universes. Each cold spot or alignment carries with it the poetry of speculation. The interior universe may have been shaped, jostled, or influenced by an external landscape, a higher dimensional environment that cannot be directly observed. In these small deviations lies the possibility of contact, a faint trace of existence beyond the observable horizon, a message inscribed across the canvas of time and space. Mathematical simulations enrich these investigations, allowing theorists to model how bubble collisions could imprint themselves upon the sky. These models suggest that the universe may bear scars of other interiors brushing against our own, disturbances echoing across the cosmic medium. Each scenario is grounded in the principles of inflation, general relativity, and quantum theory, yet remains speculative in its interpretation. The interplay between calculation and observation mirrors the interplay between interior and exterior. What is measurable offers clues about what may lie beyond, and what is beyond influences the patterns we detect within. Humanity, by mapping these subtleties, is peering toward the edges of the known, tracing the fingerprints of a greater reality through the delicate evidence left behind. At the frontier of cosmic exploration, the James Webb Space Telescope peers across 13 billion years of time, seeking the faintest glimmers of the first galaxies. Each photon captured is a whisper from an epoch when the universe was still young, a delicate signal that may carry subtle anomalies, hinting at processes beyond standard cosmology. Astronomers scrutinize the distribution of these early stars, the luminosity of primordial clusters, and the chemical fingerprints left by ancient supernova, searching for evidence of irregularities that could point to interactions with other universes or the imprint of higher dimensional dynamics. The very act of observation transforms these distant light sources into storytellers, revealing not only the evolution of galaxies, but potentially the fingerprints of realms beyond our own. Every data point is a brushstroke on a vast cosmic canvas, hinting at structure, disruption, or invisible influence that may suggest we inhabit an interior of something larger. In parallel, particle physicists probe the subatomic world with instruments of extraordinary precision. Accelerators such as the Large Hadron Collider smash protons together at near light speed, recreating conditions reminiscent of the universe's earliest moments. Among the debris, scientists search for signs of extra dimensions, hidden particles, or deviations from the standard model that could hint at higher dimensional space. The discovery of supersymmetric particles, miniature black holes, or other exotic phenomena would imply that our observable universe is intertwined with a larger geometry, a membrane within a multidimensional expanse. Each collision is both violent and illuminating a small-scale echo of cosmic processes that may govern the interiors of universes within universes. Here, the microscopic becomes a telescope into the unseen architecture beyond our immediate reality. Meanwhile, the quest for quantum gravity seeks to reconcile the classical elegance of Einstein's relativity with the probabilistic nature of quantum mechanics. Loop quantum gravity, string theory, and other frameworks attempt to describe the birth of spacetime, the behavior of singularities, and the fundamental nature of interior universes. Experiments remain indirect, relying on cosmic phenomena such as black hole radiation, the behavior of high-energy particles, and precise measurements of spacetime geometry. By merging these two pillars of physics, scientists hope to glimpse the underlying rules that determine why the interior universe behaves as it does, and how it might be connected to a larger, unseen structure. Each theoretical model, tested against observation, serves as a lantern, illuminating corners of reality where the interior might meet the exterior. Gravitational wave observatories, like LIGO and Virgo, have opened an entirely new sense with which to perceive the cosmos. Ripples in space-time, generated by colliding black holes or neutron stars, travel across the universe almost unimpeded. Beyond these dramatic events, subtle primordial waves from the epoch of cosmic inflation may carry signatures of processes beyond our observable universe. Detection of these faint ripples would provide direct insight into the earliest instance of the interior cosmos, revealing potential collisions with other universes or the stretching influence of higher dimensional fields. Scientists listen to the silence between the waves as much as the waves themselves, passing faint echoes from noise, hoping to catch a signal that points towards something beyond the bounds of space and time. We can perceive dot mapping, cosmic voids, vast empty regions between galaxy clusters, has become another frontier in this search. These immense expanses, nearly devoid of matter, may contain subtle distortions or gravitational anomalies suggesting interactions with external structures. By precisely cataloging the shapes, sizes, and distributions of voids, astronomers hope to find fingerprints of multiversal contact, the faint tug of a neighboring bubble universe on our own. Even minor deviations from expected cosmic patterns could reveal the hidden hand of something beyond, an exterior influencing the interior in ways not immediately observable but mathematically consistent with speculative models of brain worlds or bubble collisions. Simulations of brain world dynamics and multiverse collisions have become increasingly sophisticated. Using supercomputers, physicists model interactions between higher dimensional membranes, predicting observable consequences such as temperature anisotropies in the cosmic microwave background or expected galaxy alignments. These simulations create virtual interiors to test the plausibility of interactions with external realities, helping guide observational strategies and refine theories. Here, mathematics becomes a bridge, translating abstract higher dimensional collisions into predictions that can be sought in telescopic data, gravitational wave patterns, or particle experiments. The search for dark matter particles also carries implications for understanding the universe's interior and its potential embedding in a larger framework. These invisible constituents, which shape galaxies and clusters through gravitational influence, may represent leakage from higher dimensions or interactions with unseen realms. Experiments using liquid xenon detectors, cryogenic sensors, and underground observatories aim to capture rare interactions of dark matter with ordinary matter, potentially unveiling a connection between our interior and a broader multiverse. Every null result is itself a clue, narrowing possibilities and refining our understanding of how the interior is governed, constrained or influenced by factors beyond observation. Handling the vast datasets generated by telescopes, gravitational wave detectors, and particle experiments has become an enormous challenge. Cosmic signals are faint, rare, and often masked by instrumental noise or terrestrial interference. To sift through this complexity, scientists increasingly rely on artificial intelligence, machine learning algorithms capable of recognizing subtle patterns imperceptible to human analysts. AI identifies anomalies, classifies events, and predicts regions of interest where signs of higher dimensional interactions or multiversal imprints may appear. In this sense, Intelligence itself becomes a tool to bridge the interior universe with the possibility of exterior realities, allowing subtle signals to emerge from the cosmic background. Current efforts represent a delicate balance between precision and imagination. Instruments provide unprecedented resolution, theory offers mathematical rigor, and computational power allows the simulation of realities far beyond direct perception. Each piece of data, whether confirming expectations or revealing anomalies, feeds into a larger narrative. The interior universe is both accessible and mysterious, measurable yet hinting at what lies beyond. Scientists move with patience and awe, probing with telescopes, detectors, and algorithms, aware that even the smallest discovery may illuminate an entire hierarchy of interiors and exteriors previously unimagined.